I am live. Error, select the new key here. Hey! Oh. Hey, Eamon. Thanks for tuning in. You're early as well. Thank you. Can you hear me all right? Sweet. Hey, thank you, Eamon. Thank you. There's so many functions on this platform. It's crazy. Never knew streaming was so difficult, honestly. I'm using a very cheap microphone, not my computer one. Eamon, if you want to follow, there's questions down in the description. You can click on that link. It should open up to the questions that I'm running through. You can either follow along or just watch me do them. Oh, software. Yeah, right. Oh, the classic OBS Studios. I came across it. Oh, I think this other streamer was. I was watching some League of Legends streamer and they were using it, and they so happened to broadcast it, and I'm on it now. It's nice. It's quite user friendly. All right, let's start this. Oh, I realize there's a bit of lag. That's cool. All right, welcome. Hi, I'm Layman. Nice to meet you all. For those who are here, for those who are watching later on, thank you for joining me. Just wanted to wish you guys best of luck for the remaining exams that you guys have for HSC. For those who are watching this later in either in the week or whenever. This is for a HSC Chemistry 2023 revision prep. As you guys might be aware, chemistry is on Friday, this coming Friday. So today's the 21st of October 2023, and exam is on the 27th of October 2023, Friday. So my goal in these upcoming 5 live stream is to go over the top 5 questions with most marks out of all the HSC that's been done with the new syllabus. So that's from 2019 all the way up to 2022. It's honestly, it's quite interesting, the exams. If you haven't done so already, I strongly recommend you guys going through them. It's probably one of the best exams you can ever do. Chemistry is fun. I feel like I can make it fun. So I just want to quickly share this with you guys. This is just a table of all the different syllabus dot points that's been asked in the HSC, based on how many marks and overall how many, what's the average mark that you can expect from the exam. So let me take off these filters. So the real one that we're going to go through today is this one. So investigate the processes used to analyze the structure of simple organic compounds addressed in the course, including but not limited to, we've got proton NMR, carbon NMR, infrared spectrum, and mass spectroscopy. So the goal for today is to go through that, and then the subsequent lessons we'll go through the next 4. I really wish I had time to go through all of them, but just given the time restraints, you guys having exams and timing wise, I just really want to focus on the top 5. So without further ado, let's get started. So I've basically pulled off these questions either from trial papers or from HSC exams. So there's a reference at the bottom of every question. For those who came a little late, there's an exam, there's a link to this file with the questions I'm going to go through today in the description. So feel free to click on that, work with me throughout this video, or if I don't get time to finish all of it, you guys, I'll post out the answers. So let's get started on these ones. So what are you looking for when you're doing these questions? So these ones, you're trying to identify the organic molecule, whatever the structural formula is. Sorry, before I say that, obviously, this is worth 10%. Should have gone through that first. This is on average worth 10% of your HSC mark. So very important that you know this. Let's jump into it. So spectrums. It's always very interesting to understand and look at these and identify. So I guess really understanding the why first. So why is this important? Why are you learning it? There's so many mysterious substances in the world. Unless it's properly labeled, 99% of the time you don't know what that is. It might be a clear, viscous liquid, and you've got no idea what it is. It could be water, it could be jelly, it could be some moisturizing product that you add on, but you have absolutely no idea what it is. So these spectrums help to analyze, to identify by giving certain characteristics of them, and allow us to identify the molecular structure. So this question is from Norman Hurst, Year 12, Trial, 2021. This is section 2, question 7. The question reads, Joshua is determining the structure of an organic molecule. Microanalytical data shows that this molecule consists of 54.5% carbon, 9.1% hydrogen, and 36.4% oxygen by mass. So very important data there. The ion H-NMR mass spectra of compound A are shown below. So we've got our IR, our H-NMR, and our mass spec here. So first of all, this is a bit of a year 11 revision question. So how do we start this? Calculate the empirical formula. So ultimately we want to calculate the structure of it, but starting off, the empirical formula. We're given these information here. Oh, it's getting a bit bigger. So how do we start with that? Yes, so we always want to convert things into moles for us to work with. So we have mass, we want to do moles. How do we do that? Let's start. So let's find the moles of everything. So I like to treat these percentages as nothing, as just a number. So how do we find moles? We find moles. Oh, okay, that's too thick. Okay. Moles of C, carbon, is equal to 54.5 over 12.01, which is in the calculator. 54. 4.537 ... And then we want to find our hydrogen. 9.1 over 1.008. About 9. 2, 7, ... Our moles of oxygen is 36.4 over 16. .275. Now, to work out empirical formula, if you guys remember, we want to try to get them all in a molar ratio of one another. So the idea of these is we want to divide them all by the lowest number. So the lowest number is this one. So let's divide all of them by 2.275. So that would be 1. 2.275. This is about 3.9682 ... That's about 1.994 ... So if we have them all in a ratio of one another, so if we write C ratio H ratio O, we have 1.9. Sorry, not 1.9. What am I doing? We want to round them to full numbers. So that'll be 2. Hydrogen is 4. And oxygen is 1. So if we have this ratio, our empirical formula is going to look like this. C2H4O. Now this feeds into the next question, which is use the appropriate spectrum to confirm the molecular formula for the compound Joshua is analyzing. So the molecular formula. So we always know that the empirical formula is always sort of the not HCF, LCM, no, HCF, highest common factor of all of them. So in order to find the molecular formula, we look at the mass spec. Samantha, thank you for coming. Not a problem. Feel free to look in the description. You can follow along with the Google Drive file. This is the exact same file. If you want to write it with me, feel free to, or you can look back at it. So molecular formula is always in an integer value. So molecular is equal to some integer n times the empirical formula. So the formula, you can also look at the molecular weight of this one, sorry. So what's the molecular mass of C2H4O? That's 2 times 12.01 plus 4 times 1.008 plus 16. I'm sorry, the pen's really not the greatest. If there's any legibility issues, please let me know. I'll be posting out proper answers after this. So feel free to look at those or give me a shout if you need any clarification on anything. Okay, so that is equal to 44.052. Now, the molecular formula is an integer value. So we want to look at the mass spectrum. What is what we call the molecular ion peak? So I'll go through each spectrum as we go, as we are answering these questions, but please do note that sometimes you don't get these sort of questions broken down, you're just given a long response space like so. So just to make it easier, let's go through these one by one. So we're starting with the mass spectrum. So the last peak here is the molecular ion peak. So what is that peak? Why is that so important? This tells us essentially what we call the mother molecule, aka the original molecule. Now we only need to look at the last one, which is the one that's sticking up. You might see like little peaks there. They're just isotopes of they just consist of isotopes of the elements in there. So mainly in this case carbon, but we don't need to worry about that. We just really need to look at that one with the highest peak there. So that molecular mass, that mass to charge ratio is actually about 88. So we know that our integer here is 2, and we want to just times our empirical formula by 2. So that's just C4H8O2. Now does that equal to 88? Let's check. 8 times 008 plus 16 times 2, which is, calculator, 4 times 4.01, 8 times 1.008, 16 times 2, 88.104. Now, the decimal doesn't actually matter, so don't stress too much, just look at the 88 essentially. So that is our molecular formula. Cool. Now comes the juicy part, where we want to draw and determine the structure of the molecule and justify. So this is where we can come back and look at our other spectrums. So usually they'll give you the molecular mass, or they can give you the molecular formula, and you can work from there, but varying questions can have different various difficulties. So in this case, we had to work out the molecular formula. Most cases they'll just give that to you because look how much time I wasted just calculating that. So let's look at the IR spectrum. So what does IR tell you? IR is a very interesting one. So it tells you the functional groups in there. So while I pull up the chemistry data sheet, let's have a look. We can have a look at them. So the data sheet actually gives you what each peak approximately indicates what functional group. So what we're looking at here is we've got our IR spectrum. It's got this broad peak at about, I'd say about from 2500 to about 3500. We've got a narrow, strong peak at about our favorite 1700. So what do those indicate? So while I got the data sheet here, let's just write down what they might mean. So our molecular formula is C4H8O2. So we look at that and we can sort of think, okay, what could it be? What might it be? So you're typically going to get some sort of, I would typically increase the difficulty of this by usually saying like, oh, it might be an ester, it could be a carboxylic acid, etc. So what functional groups in a IR does it tell in order for us to confirm whether it's an ester or carboxylic acid, or it could be another thing, it could be a diketone, or it could be whatever, a di-alcohol, whatever. What features of an IR tells us that? Okay, so we can look at this. So I said this one was broad, and I said this one was strong. So if for those wanting to add more detail to their responses, you would want to describe the strength and also the narrow or broadness of that peak. So this one typically says 3000. Usually use where that peak is, 3000. So we would say this is 3000, and don't forget the units, centimeters to the -1 wave number. Now looking at our infrared data, CH is probably the corresponding one. So it could be a CH, could be, okay? So we always suspect. It's very hard for us to identify exactly, except for this coming one. So this one, my favorite one. It's at 1700 centimeters to -1. And what does that mean? It is the C double bond O stretching. Okay, so this tells us there's a C double bond O. We call that a carbonyl. It's an indicator that it could be a ketone, it could be an aldehyde, it could be a carboxylic acid, or it could be an ester. Now, there's another one that we want to look at to see if it's an ester. It's most likely an ester in this case, potentially, is this one in the fingerprint region. So the one in the 1000 to 1300, which could be this one. However, you're not needing to worry about things, oh, that's bad. You're not needing to stress about things within the fingerprint region that we call, okay? In the 1500 or less. But you could label that out, but it's not a definitive, it's hard to say whether that is, but it's most likely the case. Okay, so that's IR. So from our IR, we can really say there's a CH and a C double bond O. Now you might argue that this could also be a OH, okay? Let's be skeptical at the moment about it, whether it is. We'll use our H-NMR to help us to identify that. It could be. It's hard to say, but the broadness, starting to think second thoughts, potentially, okay? Let's look at our H-NMR. Now, your H-NMR typically has peaks like this, okay? It's the same as C-NMR, slightly different, a little bit more detail, okay? So there's 4 things you can look from a H-NMR, okay? So you can look at, so what does an NMR, what does an NMR tell you? It tells you hydrogen environments, okay? So what hydrogens are equivalent in terms of how close are they to electronegative atoms, or what are they bonded to so that they're equivalent, okay? Let me show you how to work this out, okay? If you need me to go into more detail, please shoot me a message in the comment section below. So how I like to write this is, first of all, I look at how many peaks there are, okay? So there's 3 peaks, like little groups of peaks. So I like to write H1, H2, H3, each denoting one hydrogen environment, okay? So I like to draw up a little table. The first thing I look at is the chemical shift. What's the chemical shift? Chemical shift is this x-axis here, okay? This is chemical shift. This tells us how close our hydrogen is to a very electronegative atom. So the most electronegative atom is fluorine. The second, and electronegative atom is oxygen, okay? That's typically the ones we see. So I like to write down the chemical shift, which is, in this case, oh, that's a very bad line. What's that? 1.2? 2.7. H3 is about 11.8. Most of the time, exams will give you all of this information, so there's no confusion with whatsoever in terms of your chemical shift and all your other data. So just look at me, do this, and you typically have this, okay? Next thing we look at is the integration. Now the integration simply means number of hydrogen in a ratio, number of hydrogens in that equivalent hydrogen environment. So what we look at here is we look at the area, okay? This is the area underneath the curve, okay? So we do this in a ratio. So I like to divide everything by the smallest number. Okay, so I'll divide everything by 0.7. So this is 1, that's 1, and that's approximately 6. Now, in most examples, what you're going to see is your hydrogen integration is going to add up to your hydrogens in your molecular formula. So we got 1, we got 1, we got 6. So that adds up to 8. So that's perfect. We know we're doing the right thing here. So my H1, which I've denoted as my Hydrogen-1 environment, is 6 integration. H2 is 1, H3 is 1. Okay, running out of little room here, but it's okay. We got this. So I'm gonna have to draw over this graph. Please, I do apologize. So after that, integration, we look at the oh god, lost the word. The splitting. Sorry, it's the splitting. What is the splitting telling us? The splitting, we like to use this rule called n plus 1 equals to the split. So your splitting could be singlet, doublet, triplet, quartet, and after quartet we typically use multiplet. Singlet just means there's a single peak, okay? Doublet just means there's 2 peaks, or splits of peaks. Triplet just means 3, 4, and multiplet just means 5 plus. So, as you can see, for H1, we've got a doublet. So, doublet, if we put doublet into the split n, now, this is where I explain what n is. N is the neighbors, okay? Let's write our split first. So we can do doublet. H2 is a septet. So septet is 7. I know multiplet, but just for clarity, that's a septet is 7. And then H3 is a singlet. Now, this is where we write in our neighbor. Sorry, I have to write over this. Now, in a normal situation, you'll have this written down in your lines here. Feel free to write that in your lines, but just for clarity and just for me being on the same page as the spectrum, I've just written it over here, okay? So, do apologize. We want to do our neighbors. We follow this n plus 1 rule, n being the number of neighbors, and neighbors is very important for us to ID exactly which environment is next to which environment. So, doublet, we sub doublet into the splitting, so n plus 1 equals to 2, n equals to 1. So, this first hydrogen has 1 neighbor. The second hydrogen environment, septet, means it's got 7 here as a split. So we've got n plus 1 equals to 7, so that's 6. Cool. H3 has a singlet, which is, the split is 1. So we've got n plus 1 equals to 1, which is 0. So we can sort of map this out already. I'm just going to change a bit of a color. Blue, sure. So we can say that we've got a 6 integration. So think about what the potential groups are with 1 neighbor next to it. Okay, so we could have this. Now your typical hydrocarbons are either in like C2, CH2, 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 etc., etc. Or your terminal carbons, the ones at the very end of the chain, they're typically CH3. So could you have 2 CH3s next to a carbon, and this carbon so happens to have a H? Would that satisfy the circled being the H1s in blue? So this will be H1 and the reds circled in H2, because that's only 1 integration, but it has subsequently in the carbon that's it bonded to, the subsequent carbons have 6 neighbors. Could that be the case? Potentially. Let's keep working. So could be? Maybe. Maybe. But we need to think about the ester group. So, what do we have here? Black. So, this could be... Sorry. I'm writing over myself. So, let me take this specifically and bring this down here. And can I bring this whole table down here? Maybe I'll just bring a snapshot of this one. we know our molecule is, oh, C4H8O2. All right. So I would say, yep, it's most likely going to be 2 times. So I like to sort of say potential groups. So this is sort of just my rough working out. When I write the response, this is where I sort of say, oh, hey, okay, maybe that's this. Okay, I would typically say H3 usually is an OH group. So it might suggest that we are dealing with a carboxylic acid. But if we are dealing with a carboxylic acid, we've got this. We don't have that one integration there. We've got one integration here, which is the OH. We don't have that second one. So that is usually not the case. So let's keep potentially working this out. So I would think this is where it comes back to, this is where having more information is really helpful. So what are we missing here? We're missing our C-NMR. So having our C-NMR might assist us a little bit, maybe, but in this case, it's hard because we don't know our carbon environments. We know our hydrogen environments, but it doesn't seem like our O's are adding up, because the one I've drawn here is we're sort of out of space, sort of. So how do we get a group where you've got your double bonded O like that? So let's have a think about this. So our molecular formula is that, yep. Our IR tells us C11O, great. OH potentially broad, cool. Integration 611. We should have a C double bond O somewhere. So what if we try? And the H is on top of that. What if we try this? Because there's no way you got this. This will give you that 6 integration, but then you're out of carbons, you've got no way to put your oxygens. This is a weird one. This is a very weird one. Okay, let's list the groups we've got. This is an OH for sure. This is a H between 2 C's, H3s. Okay. What if we've got we don't have a H2? That's the weird one. We don't have a H2. If you draw this one, double keto, you don't have enough hydrogens. But you have to have Why is there a carbon double bond? Or would that show you on the IR? What if there's a carbon? That's a good point, Sam. You typically don't deal with double bonds. Amond, what have we got there? Methyl propanoate. Sorry. If you have C there, that's it, right? Thank you, Eamon. I think that's the, yeah, absolutely. That's that. So having this helps because those are that. Where's my blue? This one? These are your hydrogens. 1. Then hydrogen 2 is this one. Then hydrogen 3, let's get this pink, is this one. Okay, I think we're ready for a response. Let's take this one out. So, how do we write a response? That's a good question. We use the information that we've got. So, let's start this. Pen, black. Okay, so let's go for each one. Let's go to IR. I like to have these in sort of subheadings. IR, I like to say what peaks they have and what they potentially might mean. Okay, so we do have an OH group, so we can say we've got a broad, strong peak at 3000 cm to the -1, which could indicate a CH stretch. Okay, that looks okay. I'll just say that's a OH stretch and a CH. Oh, CH. We've got a strong narrow peak at 1700 centimeters to the -1, which could indicate a C double bonded O. Cool. Now I'd like to talk about H-NMR last because it's always a very interesting one. From the information in the question, we identified the molecular formula to be C4H8O2, further supported by the mass spectrum. Now we can talk about NMR. So NMR, H-NMR specifically, tells us the number of hydrogen environments, as well as the groups adjacent. Yep, so I would reproduce this table and say, can either write it up again, or you can, if you've wrote it, I suggest rewrite it in again, you know, make it a bit more clearer. I would like to just reference H1. If you want to write it out in full sentences, that's fine as well. H1 has a chemical shift of 1.2 ppm, integration of 6 H, and doublet indicating it is a CH3, oops, sorry, it's a CH3, it's a 2 times CH3 group adjacent to a singular hydrogen. H2 has a chemical shift of 2.7 ppm, 1 hydrogen integration, septet indicating it is a singular hydrogen adjacent to 6 hydrogens. Now we can make that statement saying this environment is next to H1. We can even explicitly say that. That's fine. I think that's fine. You can draw it out if you like on the response paper, like you can draw it out how I did before, like this. Then we can say H3. H3 has a chemical shift of 11.8 ppm, and then in brackets we can say indicating high electronegative presence. Okay. More lines. 1H integration, splitting singlet, indicating a hydrogen adjacent a very electronegative atom, e.g. an OH. Combining them all together, we can speculate that this molecule is 2-methyl propanoic acid, and then what I like to do is draw out my molecule. And then use some pretty colors or indicate that, oh, I'm missing a H. Arrows. This is your H2. These are your H1, and this is my H3. Okay? Cool. tool. So you're sort of laying out all the information that you get from the spectrums. I find always drawing the diagram and explaining which environment is which also really helps. But piecing together the information is probably the most important part. This definitely made me very confused, but hopefully that makes sense for you guys. Let's keep moving. Let's do this one. So, a chemist finds an unlabeled bottle containing a large amount of compound Y, a colorless liquid. Elemental analysis gives us a molecular formula of this. Compound Y does not decolorize bromine, water, nor does it produce CO2 when added to NaHCO3 solution. Now, Sam mentioned a good point about double bonds. Actually, I have never seen a double bonded C question. If you have one, please share that with me. I would love to do that. You're typically going to deal with just single bonded Cs. The favorite one is to test an ester and ester or carboxylic acid. So let's go for this. IR, no broadness, so no OH, so it's only CH. We have a strong narrow here, about again the 1750 mark. So we got a C double bonded O. Okay, so most likely this is an ester. We can sort of see that is about 1300 as well. So that could be a C single bonded O. Your C-NMR, okay, great. We've got 4 environments. Now, it doesn't show us the splitting. So what we can really see from the carbon environments are how many carbon types there are, as well as what their chemical shift will tell us. So again, looking at the data sheet here, this tells us the C-NMR chemical shifts. So 170 says, okay, that is a I will move those again, sorry. Tells us that's a C double bonded O ester or acid. We know it's not an acid because there's no OH, so we just say that's an ester, C double bond O. The 68, what could that be? It could be a C single bonded O ester, again, no alcohols, not ethers. 22, 21, they're usually just the 50 to 40 range, so C double bonded C, C single bonded Cs for each of them. Now, I've just written these here so I don't have to refer to the sheet, but in the exam for you guys can look at the data sheet and reference them. This just helps me to write a response easier. Okay, and your H-NMR data, they've got this table for you, which is great. You just have to process it. We use the n plus 1 equals to s splitting, and we can work out what n is. So n doublet is 1 neighbor, singlet is no neighbor, septet is 6 neighbors. Okay, so bringing this sheet up, we don't need the data sheet anymore. We can write a response. So yeah, let's work out what it could be first. So C5H10O2 doesn't decolorize bromine water, which means that it's not double bonded Cs. Doesn't produce CO2 when added to NaHCO3, which means it's not an acid. So yep, so we can work out 4 carbon environments with 5 H's. So looking at the carbon environments versus the number of H's, number of C's really helps, saying that one of these carbons is probably an equivalent carbon with another one of these groups. So what could that be? So let's draw our ester group first. So we got that. Now, when there's less carbon environments than there are carbons, it means there's some sort of symmetry. It's either symmetry on the alcohol side, which is this side, or it could be the carboxylic side, which is this side. So we can try and error, or we can use the H-NMR to help us as well. So now I'm going to label this H1, H2, H3. I'm going to write this in the response, so hopefully that will be more give more clarity to the marker. So my H1 is a doublet, but it's got 6 H's. So that could be my equivalent carbon. So it looks like from that, again, we see a split of 2, so one neighbor. So again, we have some sort of system like this. Oop. Oop. We have something like this. So it could either be here or it could be there. And then the other carbon is, sorry, and then the other carbon has, looks like this is the other CH3, because there's 3 H's there. It's a singlet, so it's got no neighbors. So with that in mind, that could be either here or it could be there. Could be there, but we don't know yet. So for the sake of that, let's rod this out. So we know these are the only 2 parts left of our diagram. So septet 1 doesn't really help because that is just this, but now we get to the juicy part where we know chemical shift. So if you remember, chemical shift just tells us how close that hydrogen ion or hydrogen atom environment is close, how close they are to that electronegative atom. So in this case, our most electronegative atom is this oxygen here. You can argue it's a C double bond O, but the oxygen directly is a more electronegative species. So it's most likely this C is connected to this because this hydrogen is being affected with this chemical shift, aka this is hydrogen 3. Yeah. If I have hydrogen, if I have this C group on this side, it's not as electronegative. So it's most likely I have this on the right hand side next to my O, my ester O, and then I have the CH3 on this side. Okay, so drawing that in one go, what do we have? We've got C, H there, CH3, CH3. Cool. So how do you name that? Let's just double check before we move on. CH3, yep, that's our H2, yep. Let's go and write a response to label each of these as C1, C2, C3, C4. Okay, so quickly, IR. Now these are all quick. Okay, if feel free to write in full sentences, but I'm just a bit short on time, so just gonna write this in here like that. Oh god, why does this have to close up? C H. Okay. C double bond O, 1750. So you would describe the strength of these. So this would be a weak, weak narrow, strong broad. Okay, I'm not going to talk about the 1300 one, but feel free to put that in there, guys. C-NMR. C1. We've got 17 ppm. Oh, sorry, 170 ppm, which is equal to our C double bond O ester. C2, 68 ppm. C single bond ester. C3, 22 ppm, which is our C single single. C4, 21 ppm, which is our CC. Cool. H-NMR, H1, 1.2 ppm, 6H, doublet, one neighbor. This could be potentially 2 times CH3. Again, we can write that one in there. H2, 2.0 ppm, 3 hydrogens, singlet. No neighbors. this is just SH3 somewhere, H3, 5.0, 1 hydrogen, septet, 6 neighbors, which could be just a H. Cool. Yes, and then now we can put in our C1s. So I like to say each individual group, which hydrogen environment, which carbon environment they are. I'd like to label them. So this is a this could be a C4. That's a C1. Nope, that's a C3. That's your C1. That's your C2. And these are H1 and C3. And this is H3. Cool. So what do we call this molecule? Start with the alcohol. What is your alcohol? Where does your alcohol come from? It comes from a what's the longest chain? 2. So methyl ethyl. That's your methyl ethanol. Wait, sorry, what am I doing? This is a 2-propanol, so so this will be propyl 2 ethanoate. Okay, so this just is your alcohol group. This is your carboxylic group. Does anyone have any questions? I will move on with a couple minutes to go. Hopefully I can answer this quickly. Okay. CHO, colorless liquid, reacts with sodium carbonate, produce bubbles. So it's most likely a carboxylic acid. Our molecular ion peak is 74. Our infrared spectrum, could it be named 1-methyl? Can I make chat bigger? One methyl ethyl. Could it be named 1-methyl? It can so it could be methyl ethyl ethanoate, so the 1 doesn't actually have to come in. But best to name it with the number there to help distinguish that it's actually just a secondary. Oh, where are we? The secondary alcohol. Yeah. Okay. Sorry, where were we? 74 molecular ion peak. That's the OH, lovely. That's the C double bond O, we know that. So let's do this quickly. So we want a carboxylic acid with a molecular mass of 74. Now we can guess and check quickly. We know sort of it looks like this. And then we can have X amount of CH2 groups. So it could be this. Now the base of this, how much is that? That's 2 times 12.01 plus 2 times 16 plus 4 times 1.008. That's 32, 24, 36, 60. So not quite. If we add in another CH2 group, that's 14. So 60 plus 14 is 74. So we actually have this. So we have a propanoic acid, potentially. So it's always good to know what you're writing for in terms of when you're justifying, because it really helps to name it and explain it, all of that stuff as well. So let's do C-NMR first. There's 3 carbon environments, perfect. We know there's 3 there. Let's draw this out a little bit better. The 180. 180 just means the ester acid. In this case, we know it's an acid, so we just write the acid. It's the C-double-bond-O. These are just CCs. Oh, what happened? Acid, C-double-bond-Os, CCs, CCs. Hydrogen environments, 1 singlet. Let's do our little table here. Let's write this table here. H1, H2, H3. Our chemical shift is, let's say that's 11.5. H2 is 2.4. And then H3 is 1.1. Integration is 1, 2, 3. Splitting is singlet. It's quartet. It's triplet. Neighbors 0, 3, 2. N plus 1 is equal to splitting. N is the number of neighbors. No neighbors, probably no H. H2, integration 2 next to 3. Should be pretty straightforward. That's next to that. Now, which is next to that? Perfect. We've got our, oh, sorry, no, not next to that. It should be our propanoic acid. Right, so mass spec, we can say molecular ion 74. We know it's a carboxylic acid as it reacts with sodium carbonate. CO2 produced, so likely to be propanoic acid. Our IR tells us there is a OH at 3000, C-double-bond-O at 1750. Our C-NMR tells us there's 3 carbon environments. The one at 18 ppm is equal to our C-double-bond-O acid, and our 35 ppm and our 10 ppm, they are the C single. H-NMR refer to table below. CH3, CH2 together, and then in brackets I want to say that's H3 and H2 respectively. H1 is the hydroxide O in COOH. Okay, so I do want to come through this one. So that's propanoic acid, A. Explain why, and then B. Explain why chemists should use more than one spectroscopic technique to identify an organic compound. Use 2 spectroscopic techniques to support your answers. So just discussing it first, it's very important to know that each spectrum or each device or each device producing these spectrums have their own limitations. So mass spec, you can see the original molecule, you can see the potential fragments, but this is all a guessing game, what they might be. We don't know exactly what chemical compositions these all are. It could be just any possibility that the periodic table has on the atomic masses. The IR tells us functional group, but it doesn't tell us how many. It doesn't tell us where it is. So this is the plus, so the good side. Doesn't tell us how many. It doesn't tell us the location. Your H-NMR, in my sole opinion, I think H-NMR could solve most things, but the more the better, really. So the H-NMR tells you hydrogen environments. It tells you the location of things, especially how close you are to your electronegative environments, and so can C. So ultimately this answer is asking, there's limitations with individual ones, but when you combine them all together, you supplement each other. So what can the infrared spectrum do that the mass spec can't do, for example? Or what can the H-NMR spectrum do but the infrared can't? So I would say in this case I'll talk about infrared, and I'll talk about H-NMR. I think H-NMR is pretty good. Infrared as well. So let's start with infrared. So we can start with an introduction sentence. So we can say each spectroscopic technique has its own limitation. However, when used together, each technique advantages is able to supplement the others' downfall. So we can say IR is good for functional group identification, however lacks the ability to advise the location of the functional groups. And how many? So actually I'm not going to talk about H-NMR. I just feel like this response here is digging me a further hole saying, oh, H-NMR can't actually do this. So I'm going to talk about mass spec. So mass spectrum, on the other hand, allows educated guesses for the potential number of groups and lacks the ability to tell us location. I'll probably end off saying H-NMR and C-NMR could advise the potential location. Just through us working out the number of neighbors, what potential electronegative groups there is, potential location of these functional groups, could advise the potential location of these functional groups, full stop. Okay, so that's how much time I've got today. I'll post up the answers for these questions. Sorry I couldn't go through all of these. Oops, decided to freeze on me. So yeah, so hopefully you guys learn a bit today. If you have any questions, feel free to leave a comment in the video. I will do my best to answer all of them. But for tomorrow, just because you guys are here, we are doing reaction mechanisms. Bit of mod 7 today. Tomorrow, sorry. So that's worth 6.5 marks. Hopefully that will be in your exam with large amounts of marks, but as you can see, it wasn't there in 2022. Yeah, so I'll see you guys tomorrow at, I believe, 4. I'll post the streaming link on the description of this one, and I'll also update all the other posters that I've done on Facebook. But thank you guys for tuning in. Hope to see you guys tomorrow and teach you guys more